Hello everyone, I welcome you all in this lecture. So in this lecture, we are going to talk about quadrotor flight simulation. So as we did the aircraft 6 degree of freedom flight simulation. So in that lecture, we have covered the fixed wing aircraft. We have derived the equations of motions. We have written in the MATLAB and we have done the simulation, and we had a feel for a how the fixed wing aircraft behave with respect to the time. So I thought it is better to take another lecture on this topic flight simulation. I thought it is better to take a quad basic quad model here and try to understand how the quad flight simulation look like. So if you understood the quad, or in later case multi-rotor plus fixed wing, then you will be able to understand the complete VTOL and then transition and fixed wing, and it will be helpful for those who are working in a air taxi design where it can take a vertically take off, vertically land, forward transition, backward transition, right? So I thought it is better to take this lecture. So procedure remains the same. We will write the equations of motion in a body frame, because writing the equations of motion in a body frame makes your job easy. Okay, so as we did in that lecture, if derive the equations of motion, we have written 12 equations, 6 degree of freedom, u dot v dot w dot p dot q dot r dot was the 6 degree of freedom, 3 translational motion and 3 rotational motion. U dot v dot w dot, if you multiply by the mass, it becomes the force, and p dot q dot r dot, if you multiply by the inertia, ixx, iyy and izz, that becomes the moment, right? So 3 forces, 3 moments, 6 degree of freedom, kinematic equations. And then kinematics, phi dot theta dot psi dot and x dot y dot z dot. Okay, in that x dot y dot z dot, we have also learned about how to take the information from body frame to the inertial frame and find out the position of a any vehicle like aircraft. For example, u v w are in a body frame. You cannot find the x y z. You have to take a transformation from the body to inertial. This will become x dot y dot z dot or h dot. Then when you integrate, you will get the position. That is the purpose of taking a transformation from the body to inertial. Okay, these things we have covered. So now what we can do here, we can change only external forces and everything remains the same. Okay, so you can go back to that lecture, aircraft 60 degree of freedom flight simulation, and you can just change the external forces. F equal to ma, m equal to I omega dot. This 3 plus 3 6 equations are there, right? And kinematics equation remains the same for all, for this fixed wing case and also multi-rotor or quad case. So what you can do, you can change the external forces and moments, things remain the same. So the question comes, how will you change? So first understand the physics. Let's say we have a small quadrotor model in order to explain in a better way to you. So you can just name it just 1, 2, 3, 4. Okay. Use just basic science. How will you lift the vehicle? By generating the thrust using this propeller, right? So if you generate the thrust which is greater than weight, if it is the case, then the quad will vertically climb up. Okay, and when the thrust is less than the weight, it will climb down or it will descend, right? So this is the case. And how will you so one thing is clear about taking a vertical takeoff and vertical landing: by producing the thrust more than the weight, climb, less, descend. Okay, now, but the amount of thrust produced by each motor should be equal, otherwise there will be unnecessary movement. Okay, so now that means during the vertical climb or descent, t1, t2, t3, t4, t1, t2, t3, t4 all will be equal, right? And now the question is, once you achieve some kind of height, you can hover. That means T1 plus T2 plus T3 plus T4, all the thrust, sum of the thrust equal to the weight, hover case. Now, another question comes, how will you take a moment? how will you generate the moment? So this is very simple. When you increase this motor thrust 1 2 3 4, if you increase 3 4, decrease 1 and 2, you can take a roll right direction. Right direction considered to be positive, because if you take a curve, this thumb is pointing towards the positive x-axis, so this way you can take a right roll. Okay, so I can take the right roll by increasing this 3 and 4 rpm and decreasing the 1 and 2 rpm. That is clear. And we have a more thrust, and let's say cg is this point, so force into distance becomes the movement. That is how you will get. Okay, now this is a positive roll. Similarly, if you increase this to decrease 2, this will take a left roll. Now if you increase this 2 and decrease this 2, the pitch down. That is how the quadrotor moves forward. And when you increase this 2, decrease this 2, it will become backward. That is how take a backward. You can take a quad backward or multi-rotor backward. Now the very important point, how will you take a yaw? So you know that when any propeller is spinning in opposite direction, it will produce the torque. Okay, so let's say this 1 and 3 is rotating in a clockwise. So that means anti-clockwise will be torque will be generated, and this two rotating in a anti-clockwise. So the diagonal one will rotate in the same direction, clockwise and anti-clockwise. So if you increase this 2 rpm, this is a clockwise, and decrease this 2 rpm is anti-clockwise. So rotating in this direction, right? So net, what will be the torque? Opposite direction. So that is how you can take a yaw, by increasing this 2 rpm, decreasing 2 rpm this way. And how will you take this yaw? Positive yaw, increase this rpm and decrease this rpm. That is how you will take it. Yeah, so vertical takeoff, descent, hover, roll, pitch and yaw is clear. Okay, and in one of the lecture in aerospace engineering course, I have also explained to you about the internal things, like for example, when you take a joystick, when you give the command, for example, uh, vertical takeoff, landing, roll, pitch and yaw, it is going to the flight computer will compute the command, and it will send to the motor through the ESC, and the ESC will control the RPM, I mean to say. Okay, and that is how you will take a desired, you can move in a desired direction, and you can orient your quad or multi-rotor in a desired angle. Okay, so this is all about this. So now we will go to the actual implementation in a MATLAB and Simulink, and we will have some kind of feel how the quad can fly. And if you understand the quad, simple 4 rotor, then you can add 2 more rotor, become hexa, 2 more rotor become octa, and you can decrease even, become tricopter. Okay, so once you understand the physics behind it, you can do the simulation for a mini rotor case. Okay, so we'll go in a MATLAB and Simulink, and we'll see how our quad will fly. Hello everyone, now we are uh, going to do the flight simulation, and we are going to check how the quadrotor is behaving in a MATLAB and Simulink environment. Okay, so again I am requesting you go back to my aircraft 6 degree of freedom flight simulation lecture, understand how I have written the MATLAB files, and what are the functions are there, and how I have implemented the fixed wing flight simulation in a MATLAB and Simulink environment. Then you will be able to connect this lecture in a more appropriate way and more good way, I need to say. Right? Now, first file here you can see this is called initialization. That means you are going to start the simulation. You have to define some initial state in order to run the simulation. Okay, because already I explained to you that in a MATLAB simulink environment, you can use RK4 method to compute the next stage of an aircraft, next time state. Okay, and for that you need to know the previous state. So that is why you need to initialize. Okay. Now here UVW are the body axis velocity, PQ are the body axis roll, pitch and yaw rate. Phi theta psi is nothing but the attitude.
phi is a pitch angle, theta, phi is a roll angle, theta is a pitch angle, and psi is a heading angle, and x, y, h are the position, where h is a altitude. Okay. Now, here you can write x naught, v, w, p, q, r, phi, theta, psi, x, y, h, and you can define u naught, v naught, w naught, p naught, q naught, r naught, phi naught, theta naught, psi naught, x naught, y naught, and h naught also. Okay, instead of just typing v, w, etc. Okay, so when you run this, you can see this already have run this file. You can see this, the variable will appear here. Okay, again I am clearing this, clear all. Okay, and again I will run. Okay, so that you can see how it is. Okay, once it is done, then I will go to the Simulink file where I have created everything. Okay, so in the initialization file, you can put the initial condition here x now. Okay, so that is the purpose of that file. Okay, now I explain one by one about this Simulink environment. So first thing, I have written the equations of motion. So you can go back to my lecture as of degree of freedom, and you can see how I have written this 12 equation. P dot Q dot U dot V dot W dot P dot Q dot R dot phi dot theta dot psi dot, and this X dot Y dot Z. So you need to change only external forces, right? This Fx, Fy, Fz, and moment Mx, My, and Mz. Okay. Rest of the things remain same only. Okay. Now, how you can write, since there is a no Fx forces, you can put 0. No let Y forces, you can put 0. Okay. Now, because your thrust vector is pointing in upward direction, right? When you take a chord, so there is a only upward force will be produced by the chord. Okay. By changing the force amount, you can actually take a moment. Already I explained to you. Okay. So that is why Fx Fy has been put 0. And again, I am saying you these equations I have written in a body frame. Okay. So you go back to that previous lecture. I mean to say aircraft 6 degree of freedom lecture. Understand the complete dynamics part, derivation part, etc. And here you are going to change only external forces. Okay. Because that external force corresponds to that fixed wing aircraft. Now here just a multi-rotor. Okay. Or for our case is called. Now the FZ you can write K omega square. Omega is nothing but the omega square. I have to do it, right? And KT1 is a thrust coefficient. This thrust coefficient, basically you can actually find out the blade momentum theory. So I have used here blade momentum theory to derive this K omega square. Later, when you consider the bigger size aircraft, then you can I mean to say quad or hexa, then you can actually you can use blade element theory instead of blade momentum theory. All right. Okay. So K omega square is nothing but the thrust. Uh, one denotes for one rotor, two denotes for two, third for three for third rotor, and four for fourth rotor. Okay. So this is the negative sign indicates that our z axis is pointing downward. Okay. That is why it's a negative axis like that. Now this is the xz part. Okay. Now when you have some kind of tilt, there will then the angle will appear here. So as of now, I am um, we are assuming that there is a no tilt in the rotor. Instead, it is fixed towards the uh, desired mount, and there is a no angle between the body z axis and what you can say thrust line, right? That is why you see there is a no angle. Okay. Now mx, how can you write? So already I have denoted that is 1, 2, 3, 4 rotor number. Okay. So by increasing the rotor number 3 and rotor number 4, you can actually get a force in, and by decreasing the 1 and 2, you can actually get a force, but there is a difference in the force multiplied by the distance L. So L is the distance between the rotor, you can say motor hub and CV, okay, perpendicular distance. So this force produced by rotor number 3 and 4 multiplied by the distance, and this is the force corresponding to rotor number 1 and 2 multiplied by the distance. Take a difference, you will get the positive roll moment. Similarly, by using the rotor number 1 and 4 multiplied by the distance and rotor number 2 and 3 multiplied by the distance, so if you increase this to RPM 1 and 4 and decrease this RPM 2 and 3, you will get the positive pitch, right? And similarly, when you increase or I mean to say diagonal pair of a rotor and decrease another diagonal pair of a rotor, you will get the yaw moment. Depending upon the which diagonal you are increasing or decreasing, you can get the positive and negative yaw. So these three forces and these three moments you just have to replace in from the capacity degree of freedom lecture, and you will get the ecosystem motion for a quad case. Okay, and here you can actually add 2 becomes hexa, another 2 becomes octa, and you can decrease 1 is become tricopter. So all the forces and movement you can model and you can write. Okay, so if you have any doubt in this, you can actually ask me, because these things already I have explained to you in that lecture, which is the new in this lecture that I will only explain. So omega s1 nothing but the omega square, matlab RPM square, omega square 1, omega square 2, omega square 3, omega square. Okay. This KT1, KT2, KT3, KT4 are the thrust coefficient. L is a moment arm, KD is a drag coefficient. Okay. You can say torque coefficient. So this is 1.3858 into 10 to the power minus 6, and KT1, which is equal to 234, is 1.3328 10 into 10 to the power minus 5. Mass of the quadrotor weighs 1.4 kg, IS is 0.05 kg meter square, IYY is 0.05 kg meter square, IZZ is 0.24, and since we have all axisymmetry, so I will be 0. Okay, and if you can include the drag term also, then the density becomes the important factor, and this density you can find out using this atmospheric model. You will supply the altitude, and here you will get the temperature, speed of sound, pressure, and density. So you can density you can take it out. Okay, so no problem. Now, so we know that when you supply this control input and when you completely model the drag, you can supply the density. Okay, the more important point here is control. You will able to run this, right? So now the question is comes, how will you design the control? Okay, like for example, when you take a remote, when you I mean to say that also I explained in one of the lecture, when you move the stick, how the RPM will change. So that means what is actually happening when you're moving the stick and all, is actually going to the flight controller, and what is sitting inside the flight controller, generating the command. RPM is increasing and decreasing, and you are getting what you want actually. Okay, so that comes the concept of controller. Okay, so here I have used, I mean to say, attitude and altitude controller, where I can supply directly phi command, theta command, psi command, and in more advanced case, this command also can be generated using the velocity loop, and then velocity loop the command can be generated using the position. Okay. When you include complete navigation, that thing will come. Okay. So now as of now we have commanded 100-meter altitude, 0, 5, 60-degree pitch, and no hidden. This is a PID block directly you can use, or you can actually write your own PID and you can put it. Okay, I mean to say. For example, like you can design KP, KI, and KD, and you can actually form a PID controller here. Okay, or you can just type the PID. You can use the PID controller like this, or PID controller. This is more easy. Here you just supply the reference value and you can just supply the three gain P, I and D, and here also you can take supply the PID gain. Okay, but here you need to find out the error and supply, and here the error will be automatically computed using this reference command, and actual signal will go to here and reference will go to here. Okay, and if you want to design your own controller, what you can do simply, you can actually, as I already explained to you, how will you design the PID controller. Okay, so you can take a this sum block. Okay, let's say you can supply some command. Okay, so the error, okay, when you multiply by this error, this h command minus s will become the error. You can multiply by some gain, that becomes the proportional one, and then you can take a some percentage of a proportional value, and you can use integrator here. Okay, and then you can add derivative also, and again you take a sum injection, and you can finally the output will be this only. So whatever you are writing here, I have written this P, this is I, you can change again, no problem. You can take a 30 percentage or 5% of this P value. Okay, and you can supply, you can add one more summing block here with the derivative, like 1 by s I have written, you can take just s. Okay, and that becomes a derivative, and you can sum. So whatever you are getting the output from here, the same is this. So whatever this block, this complete block, this is nothing but this one. Okay, and if you remove, if you include this summing junction, this plus and minus part also, that means error part, this becomes this one. Okay, so like that, there is a altitude loop, this is a roll loop, this is pitch loop, and this is reading loop, and this is a saturation block. So 43.5 is upper limit, and max to max you can up the number. Okay, that means 0. Okay, this limit you can decide, like for example, let's say your weight, your quadrotor weight is 2 kg, so you can design that, you can design the, or you can select the motor which can produce double of that weight and thrust double of that weight. So based on that, you can actually put the limit here. Okay, so this you have to put in Newton. So for example, let's say I have a 2 kg weight of a quad. So 2 into 2 becomes 4, 4 kg. 4 kg into Newton, that means roughly you can multiply by 10. So 40 will be the upper L. Okay. Similarly, you can place the moment limit also. That much moment, I mean to say, it can produce. Because it is important to put the saturation limit here, because it is a controller is a mathematical block. In some cases, it will compute more than what is the limit of the motor has. So in order to make the things practical, you have to put the position limit, and you can put the rate limit also, actuator dynamics, many things you can do in order to make the things as real. Now, this is the required force. This is the force. U1 is the force, U2, U3, U4 is the moment. So finally, this moment you have completed in order to get the desired motion. Desired means what? 100 meter altitude, 0 degree roll angle, 60 degree pitch, and 0. degree heating. These forces which you have desired force computed, who will provide this kind of desired motion? Finally, it will go to the motor, right? It will spin and it will produce the desired thrust, desired movement. Okay, so that is why you have to use the control allocation matrix in order to convert this force and movement into the required RPM. Okay, so here is the control allocation matrix. You can see that in first row, you can see the thrust part, this is roll part, this is pitch part, and this is yaw part. Same logic is applicable here also. By increasing the 3 and 4, decreasing the 1 and 2, you will get the positive rule like pitch and yaw case also. And vertical climb and vertical landing. Okay. Again, you have to put the RPM limit. You can put here, I put 920 into 920. Okay. Finally, the controls will be generated and this control you have to supply. Okay. Additionally, you can see I have taken the controls square root and in order to convert radian per second into rotation per minute, you can actually have a feel for what kind of RPM you are getting. But here you have to supply in radian per second. Okay. Now, this is the integrator, this is the H dot block. You can see the derivative also, not a problem. And this is the final result. You can see all the results, UW, PQR, phi theta psi, XYZ. Okay. Now it's time to run the simulation. Okay. So what we have commanded? So just note down, we have commanded 100. So let's see whether the altitude we are getting 100 or not. So see, we are getting the altitude beautifully 100. By changing the gain, you can actually make a response fast. Okay. By increasing the gain, you can make a response fast. Adjusting the derivative, you can gain, you can make this response smooth. Adjusting the integral gain, you can make the steady state uh, close to zero. Steady state error. Okay. So finally, 100-meter desired angle we are getting, and what the theta? 60 degree, beautifully 60 degree within a 10 second we are getting. Okay. And what kind of RPM value? Here you can see the RPM. You can see the RPM. Okay. Rotor number 1, 2, 3, 4 RPM. Right? Now, let's do the another test. You can make you can command 60-degree roll or let's say 30-degree roll, and I do not want any pitch. Let's say we'll get or not. Okay. So you can see phi 30 degree I am getting perfectly. And usually by changing the again you can tune the response. And theta 0 degree I am getting perfectly. This is 10 to the power minus 14. That means from the starting it is 0 only. And this is RPM perfectly. No problem. And let's say you want to take a yaw. Let's say if I command 45-degree yaw, let's say how it is happening. So I need to go and check psi, right? So this is 45-degree perfectly. Okay. Every time you have to see the RPM making sense or not. Okay, perfect. All right. And then if you want to change the altitude from 100 to let's say 500, you can check. Okay. Perfectly, we are getting 500. By changing the gain, you can actually minimize the overshoot. By changing the derivative gain. Okay. And by changing the proportional gain, you can make the response fast by increasing the gain. Okay, and by adjusting the integral gain, you can minimize the steady state error. So all in your hand. Okay. All right. So here, whatever so far we have discussed, I mean to say, if you have any doubt regarding how this control loop is written, about this position limits, about this desired variable and this actual variable, okay, about this control allocation matrix, about this block, about this equation of motion part, okay, result section, okay. I am available to solve your doubts, and I will upload this file as it is in a Google Drive, and I will put the link in a description box in YouTube. You can go there and click the link. I will give the access. You can download. You can play with this code. Okay. You can make it hexa, triquarter, octa also. You can combine with fixed wing. Okay. And you can have it perform the vertical takeoff and landing, and then forward backward transition, and then to. However, in future classes, I will take this complete hybrid aircraft simulation. That means simultaneously I will do the vertical takeoff and then the transition and then finally cruise flight. But anyway, you can use this code. You can use the previous code, fixed wing aircraft. You can play with this. If you have any doubt, please ask me. I will be happy to solve your doubts. All the best and thank you so much.